Hello, everybody, and welcome to another One World colloquium of the Psychonomic Society. I'm Stephen Lewandowski from the University of Bristol. I'm the chair of the Communications Committee of the Society, and my job today is to introduce our speaker and co-host, Beatrice Kuhlman. As usual, Beatrice is going to handle the Q&A period at the end of our speaker's talk. And our speaker today is Karla Evans from the University of York in the United Kingdom. She's an associate professor there, and she received her PhD from Princeton, working with Anne Treisman. And she then performed postdoctoral research at MIT, working there with Nancy Canwisher and Jeremy Wolf. Now, her main interest lies in understanding how perceptual information within and across senses and memory gets integrated into a unified, complex percept of the world. And that turns out to have some exciting real-world implications relating to radiological images, and the Cancer Foundation and EPSRC, I believe, in the United Kingdom are currently funding her work on that. So we look forward to hearing from Karla, and the floor is yours. You need to unmute. You're not unmuted yet, sorry. Now
I am. Excellent. Well, it's a great honor and a pleasure to be asked to give this lecture series, and I hope I live up to that honor. Today, I would like to tell you on the topic of all one sees in a blink of an eye, from natural to radiological images. So visual awareness of complex environments and findings would suggest is the result of two visual processes employing different visual attentional mechanisms. One is very rapid, unfortunately, completed in a blink of an eye, requiring no eye movement or selection. Something like that you are probably experiencing when you're viewing this rapid visual presentation of images and trying to see if you can spot the beach. In visual scene jargon, this is referred to as extracting the gist of the scene. The other process is employed when scrutiny and object identification is required, which in turn instigates eye movements and selection. Most theories of visual awareness would agree that the two processes are qualitatively different, yet both contribute to what we are visually aware of when we are viewing the world. The act of recognizing an object in a scene is filled with other objects, requires directing attention to that object. Using visual attention to select that object permits the basic features to be bound so that the observer can appreciate the relationship between these features and perceive an object like this tree. It also allows to explicitly recognize the object. So instead of just saying, I see a boy, in this case, I can say, I see my son at 2 years old. Lastly, it affords us the ability to localize objects in space, like finding the dice in the current cluttered scene. But when an observer first sees a scene, its features are unbound and its objects are not explicitly recognizable. However, as you might have experienced a few slides before, in a single glimpse, observers can categorize a scene, for example, this beautiful scene of shambles in York, estimate properties of ensemble of objects, for example, extract the average size, the average color, the average movement of these dots if they were moving. And they can detect one or two objects based on what we are referring to as diagnostic mid-level features. For example, you detect a wing, and that must indicate that there is a bird in a scene. So this type of information is central for efficient assessment and orienting in complex environments. The hypothesis is that this ability is most likely based on our extensive experience with the regularities of the natural world. Today, I want to draw your attention to this very rapid way of processing complex information that we acquire only in the blink of an eye. I will show the results of studies that give us more information of how this type of processing might function when we encounter real-world scenes. Then I will try to make an argument that the same visual system machinery can be applied to medical images that are a specialized class of scenes. And lastly, I will finish with making the argument that what we can perceive in a blink of an eye can give us more than just the ability to orient ourselves in the complex environment. So let's start with what we know about these two processes. Findings would indicate that the GIST processing is a very rapid process that works on global image characteristics without real access to location information. In contrast, the slower object identification process requires eye movements, and is based on local information, but allows us access to location information. Some research has postulated that because GIST extraction is so rapid, that it most likely is extracted in a feed-forward sweep through the visual system hierarchy, and even that no attentional mechanism is needed to be employed. To test this, we made a prediction that if this was the case, that no attention is needed, is that observers would not need to know a priori the object, the category that they're looking for. So we designed a rapid visual serial presentation experiment where the target was forward and backward masked, and you on each trial were cued with one of the 9 categories to categorize. In one case before the trial, in other cases after the trial. What you will notice from the results presented on the left-hand side of the graph, which shows performance measured in D prime, where 0.2 is chance, that there is a significant difference between whether you know a priori or after what you're looking for. So there is some form of attention needed. However, we also will observe that our participants could rapidly extract information about multiple categories, and this multiple non-selective processes accumulate information about different properties simultaneously, because the pre-cue is post-cue is significantly better than chance. Now, what is more, we see that this extraction of GIST is very flexible and task contingent. That is, depending on what your task is, extractum of GIST will be modulated. For example, if you look at this performance, these graphs showing the performance, you'll see that when one asks, is there a beach, and there is only one scene, one category present, you have no problem to rapidly detect that. However, if one adds to a scene of a beach another category that is not currently task relevant, but was at some other point, we will see destructive interference. That is, your performance will go to chance. Changing the contingency to beach and dog, or beach or dog, again changes our responses. That is, you are getting better performance. So this interaction can be constructive or destructive, depending on whether the presence of one category can be taken as evidence for or against the presence of the other. Although remarkable amount of information can be extracted from the world in a very brief time, people's understanding of contingencies of the world clearly influence how they use this information. Another hypothesis we wanted to test is the idea that GIST is a global process that does not allow precise location information. My previous work showed that observers, when reporting on GIST, would have difficulty localizing the target they were able to detect. To test this, we used functional magnetic resonance imaging while our observers we're extracting gist in a rapid, of different categories in a rapid manner and trying to localize where in space was this gist. As the results plotting the bold signal change in the early visual cortex show, there is actually no differentiation. That is, there is no part of the early visual cortex that differentiates between response types, hits, false alarms, miss, or true negs, no responded specifically to the percept of the gist target, the category. This would indicate that gist perception does not depend on feedback connections to the early visual cortex, or that observers cannot access location information from retinotopically organized cortex. If you recall, gist extraction and object identification not only work on two different spatial scales, they also work on two different time scales, a very rapid one and a slow one. And it is not easy to untangle as to how they might work together. So how these processes work together to bring about visual awareness in the external world is the topic of our next series of experiments. So one possibility is that the two processes work in parallel, the selective and the non-selective, or the distributed or focused, and we would, if they work together in parallel, one would observe no cost in performing these two different tasks simultaneously. If, on the other hand, as depicted in the diagram at the bottom of the slide, the two processes worked in a serial fashion, then we should see a cost when we require the two processes to be happening at the same time in a very restricted time frame. And something that we often experience in visual awareness, the sense that it is happening at the same time. To test this, we used a dual task paradigm in which we had our participants perform two tasks, a primary task and then added on a secondary task. The primary task could vary in nature. That is, the stimuli would not change. They will be the same. You would see a field of dots moving in a certain, to a certain extent, in a coherent direct motion in one direction, with a dot with a slightly different contrast in the middle of the field moving in a certain direction. The task would change the situation. That is, in some cases, we would ask you about the global movement of the dots. In others, maintaining the same display, we would ask you about the direction of movement of the smaller contrast dot. Now, we would equate the performance on both of these tasks, so participants perform equally when the tasks are the only task they're doing. And we also then looked at that performance. This performance is shown on the dots that are on the gray dotted line. And as you can see, the blue and the green have the same level of performance. We then introduce a secondary task, which is in nature similar to the global movement of the dots. That is, we are asking the participants to categorize the scene that slowly appears and disappears during a very brief time of the dots presented. Once we employ the secondary task, we see a different pattern of results depending what your primary task is. So if your primary task and your secondary tasks share the type of processing, we see only a slight reduction in performance between a single and a dual task condition that is explainable by the fact that you're doing a dual task. However, when the primary and secondary tasks are employing two different types of processing, then we see a significant drop in performance in dual task that is significantly different than in the other condition. To make sure that this observation is robust, we again employed a dual task paradigm, but this time introducing a different secondary task, in this case, requiring more focused attention by and focal processing by asking in the secondary task our participants now to localize a pre-cued object in the scene that they will see to one of the 4 quadrants. In this case, the pattern is different. That is, it shows that, again, when 2 different tasks are employed, we see a significant drop in dual task performance as opposed to when the same processes are employed. So the pattern of results again indicates that these 2 processes are engaged in a serial fashion, even though one after the other, even though we do not experience this seriality in our everyday visual experience. Now, our hypothesis is that our brain develops a set of general perceptual rules of expected spatial regularities for each gist category based on previous experience. These are flexible enough to generalize across variations, but specific enough to allow it to distinguish a beach from a river or a normal from an abnormal mammogram. Radiologists and other medical image experts, by virtue of their training, can extract the gist of medical images. There is ample evidence from previous work, as well as my lab's work, that the radiologists can extract what is referred to as the gist of the abnormal from chest radiographs, from mammograms, from micrographs, and from prostate multiparametric MRI. This brings us to the translational work I have conducted and my argument that medical image experts are using the same type of processing that we use to extract gist from real-world scenes to the medical images, and that through training and experience, the same system tunes itself to detect what we refer to as the gist of the abnormal. How do we test this? Well, we test this with what we're calling a flash paradigm, in which radiologists will see a series of different images, up to 200 different cases. In each trial, they're shown a fixation cross, then a micrograph or a mammogram or a radiograph is presented for a very short time, 500 milliseconds or less. And then we mask that with an outline, white outline, or just one screen, asking them first to localize where they think there was an abnormality, and then to rate on a scale of 0 to 100 as how likely do we see the abnormality. We wanted to test, is this really true, or this is a result of just selective memory in being able to remember when you've in a flash detected that there was something wrong. So our first results showed that indeed radiologists can do this for very subtle cancers above chance, even at 250 milliseconds. Now, what I'm showing here is an ROC curve that is plotting false alarms against hits, and the dotted line or the diagonal line indicating chance. This is how I will be presenting the data for the rest of the talk. So we can see that at different times, radiologists still beat chance. So one of the reasons why radiologists, especially for mammography, require to see both images at the same time, so bilaterally, is because they strongly believe that the symmetry between the breasts is very important. As a vision scientist, you would also assume that symmetry might be one of the clues of where this gist signal might be. So obviously it's not symmetry of shape or size, because women's breasts are different between each other, and also the pressure applied to them on mammograms or acquired is very different. So to test this, we wanted to see what happens to the ability to extract the gist of the abnormal when we present our radiologists with mammograms from the same woman as opposed to mammograms from 2 different women. We tested 2 different asymmetries. One asymmetry by substituting the breast with a lesion, and another asymmetry by substituting the breast that is contralateral to the lesion. That is, the breast doesn't have the lesion, but it is from a woman with a lesion. The results are plotted on ROC curves at the bottom of the slide. The dotted lines represent individual radiologists' performance, where the bold line represents the average performance, as well as indicating the D primes. As you can see, in all cases, performance is above chance. However, there's a drop in performance, indicating that symmetry is, while contributing to the gist of abnormality, is not what is the signal of abnormality. Interestingly, when you show these same images to an AI, it shows the same pattern of results. That is, the performance, even though above chance, decreases, though to a lesser extent than it does for radiologists, indicating that what the machine learns is obviously different slightly than what is the gist of abnormality for radiologists. Now, moving on, another indicator of cancer, or strongly correlated with detection of cancer in radiology, is breast density. That is why radiologists, when they assess any radiographs, also give an assessment of the density of the breast. It spans the 4-point scale, where number 1 indicates that the breast, it's a fatty breast, so low density, 2, 4, which indicates extreme density. Extreme density is strongly correlated with presence of cancer. And one important question is to see if our radiologists are really detecting the gist of abnormality, or they're just detecting breast density. If we look at the assessment of breast density and our ratings, we find no correlation with our ratings assessment of density. What is more, if we use that density as a signal, we see that if it was used as a signal, radiologists would not be able to do this detection of gist of abnormality. Another interesting aspect of this gist of an abnormality is that even though radiologists can detect it with the very subtle cancers, they are unable to localize where that abnormality is, because when we ask them to localize, they are at chance, even for when they are highly certain that there is an abnormality, which would indicate that this signal of abnormality is sensitive to global characteristics of the image, thus a global signal. We also have converging evidence for this, comes from our studies, that when we used unilateral mammograms, so that showed just mammograms of one breast, and compared performance when we showed a breast with a visible lesion, as opposed to showing a breast that's contralateral, so no lesion yet from a woman with cancer, we see that in both cases, radiologists can detect that there is that the case is abnormal, though to a lesser extent for the contralateral, but still there. Indeed, radiologists can recognize the gist of abnormality even in patches of abnormal mammograms, both which contain the lesion and also those that do not contain the lesion. We showed this by taking patches from mammograms with the lesion present, and then patches from the ipsilateral mammogram, that is mammogram that has the lesion but is not a lesion site, as well as patches from mammograms that are of the same patient but the opposite breast. And as you can see from the ROCs plotted at the bottom of this slide, we see that in all cases, radiologists can detect this above chance, indicating that this is most likely a global signal. This brings us, if it's a global signal, then spatial structural regularities must be playing a big role. To evaluate this, we use the same patches and applied a texture model, the Portilla-Simoncelli texture model, on them by training the model on those patches, and then having the model generate synthetic textures, which, while losing the local information of the lesions, still maintain the spatial structural regularities of the mammograms themselves. We took patches with the lesions as well as ipsilateral and contralateral. And the first thing to observe in these ROCs, on the left-hand side, you have the real patches, and on the right-hand side, synthesized, is to notice that when there is no local information, real and synthesized patches allow radiologists in both cases to detect the abnormality above chance. However, when there is a local information, it is additional information for radiologists. That's why we see, even though in synthesized patches, they are still performing above chance, the performance is increased in real patches. So spatial regularities, this textural aspect, is important and contributes to the gist of the abnormal. It is also useful to know that we ask our radiologist also to assess the density of these patches, and the density given to the synthesized and real patches did not differ, which is very encouraging. So we've managed to replicate that. Given that we are exploring image characteristics that afford radiologists this ability to detect global pattern indicating abnormality, it is logical to explore the role of spatial frequencies in the image. In real-world scenes research, the jury is still out as to what spatial frequencies might carry the gist signal. So we wanted to test this question in medical images. So we took a same set of cases of mammograms and either low pass or high pass filtered them, taking out either low spatial frequencies or high spatial frequencies at one point, and looked at their performance. You will notice from the ROCs plotted the left-hand side of the slide that in all cases we had above chance performance, with low spatial frequencies really doing very poorly. However, to our great surprise, the high spatial frequencies performance was comparable to completely unfiltered images, indicating that the gist might be in the fine detail. More recent work has shown that we can isolate maybe the exact high spatial frequencies where that might be happening. If we make sure we contrast, normalize, we see that performance between 0.5 and 1.5 cycles per degree high spatial frequencies seem to contribute very strongly to the gist extraction. They are also especially important for certain critical cases. I'll come back to this further in the talk. Often in literature, global processing is equated with holistic processing. Whether one agrees or not, we wanted to explore this, if this ability in discriminating normal for abnormal mammograms might be a form of this learned holistic processing. So we employed what is often employed in testing holistic processing. We employed the inversion paradigm, in which if an image is thought to be processed holistically, once you invert it, inversion will interfere with holistic processing and performance will be degraded for the inverted image. So we employed the inverted image paradigm with our mammograms, as well as using faces as a control. And we asked our radiologists to assess the presence of abnormality in mammograms, upright and inverted, as well as discriminate whether the face was a happy or neutral expression in upright and inverted faces. We looked at experts and residents. First thing that you will notice in these graphs that are plotting sensitivity, is that for faces presented here, we see that both for experts and residents, we nicely get the inversion effect, that is worse performance on happy versus neutral for inverted faces. However, for mammograms, we get an advantage for experts, but very critically, we get the inversion effect for experts where this is absent for residents. So However, one very important caveat is that these images were presented for 1 second, which is a very long time in the GIST world. So our argument is that GIST processing, while we see the inversion, is really not holistic processing. And that is because when we present the images for GIST time, which is 250 milliseconds, we see no inversion effect for the experts. So while GIST is not holistic processing of mammograms, we believe, is part of the medical perceptual expertise. Further evidence that GIST is something different than holistic processing also comes from this study, where we tested what happens if we extend the exposure time. Would that change the strength of a signal? And so we had the radiologist detect the abnormality in mammograms either for 500 milliseconds, or we gave them unlimited time, asking them to go with their first impression. And we don't find any difference. That is, exposure time neither increased nor decreased the ability to identify the gist of abnormality. No improvement in their performance. However, we did notice that that radiologists become more conservative, especially when assessing making these decisions, especially when there was no visibly localizable lesions. So how does the visual system tune to this gist of the abnormality? To investigate this, we kind of changed tack and did experiments with naive observers instead of radiologists. We took a group of naive observers and asked them to complete 9 adaptive training sessions viewing 4 categories of unilateral mammograms: normals, ones with abnormals with obvious abnormalities, ones with subtle abnormalities, and ones that had no visible abnormalities but were from women that had cancer. And they would receive only categorical feedback. That is, if they gave us a certain rating, we'd say, yes, there was an abnormality, or no, there wasn't, without indicating where and what made it an abnormality. We tested performance pre-training and post-training, and a week after on the 200 set of 200 mammograms, which they viewed only for 500 milliseconds without feedback. So the first thing that we observe is that during the training, we can see an increase in target detection. So the hits plotted here with the green line. But we also see an increase in false alarms, though markedly smaller. And looking at these results and post-test results, we find that a subset of 9 out of 15 observers that we label learners also showed a positive correlation of D primes across training and improvement in the performance between the pre and post training. Now, critically, learners also learned to detect abnormalities in mammograms that only had what we call a global signal. So though no lesion, but a mammogram from a case with cancer. But this, as you can see, improvement is not well retained. So we conclude the gist of abnormality indeed can be learned from perceptual incidental learning in mammograms, both with and without visible lesions, obviously due to individual differences. However, there is poor retention, which suggests the perceptual tuning to gist needs maintenance. And there is converging evidence from our findings with radiologists that gist performance is actually correlated with the number of cases they review per year, not the years of experience. So it's that perceptual exposure, that perceptual learning that makes you tune into your system, tune into the gist of the abnormal. So our findings support the idea that gist extraction abilities can develop separately from medical knowledge, and can be developed through very simple perceptual training paradigms. Now, breast cancer is widely agreed to be the most prevalent and deadly cancer in women worldwide. As with most cancers, early detection is vital, as it allows for treatment before disease progresses and improved clinical outcomes. Now, clinical breast exams and digital mammography, as they are effective and cost-effective, have been estimated to reduce mortality by 30 to 50%. So is it possible that the signal that the radiologists extract in a blink of an eye can be used for this critical early cancer detection and save lives? And we have results to indicate that yes, this is very much so. In two separate studies, we indicate that based on momentary glance, so GIST, radiologists can distinguish some mammograms of women who were reported as normal, but diagnosed 2 to 3 and up to 5 years later with breast cancer at subsequent screenings from obviously mammograms that are women that don't show cancer. And in both cases, this extraction was really not linked to years of experience, but rather years mammograms seen within a year. And we can see it goes across different radiological approaches. For example, both we see the extraction of GIST in priors, so years prior to onset of any visible cancer, with US radiologists, with UK radiologists, as well as with reading radiographers. So people that do not have medical training, per se medical training or medical degree, however, have a year of training to screen for cancer, and they are as good as radiologists. So clearly this ability to see the gist of cancer is a learned skill. Not only can we train novices, but data from radiologists indicate that it is a perceptual rather than a medical skill, since even detecting the abnormality in mammograms years prior to onset of any cancer is significantly increased when radiologists, it's read by radiologists that read at least 2,000 cases a year. We can increase that signal from 0.2 D prime to 0.88 D prime. Also, it is a skill of detecting a signal that we think can be enhanced because we have results that suggest that certain high pass filters might intensify these very subtle global texture patterns that are most likely the ones that are providing the signal for radiologists to say, there is something abnormal here, even though there is no visible signs of cancer. So one might say, okay, this is a robust signal, I believe you, but it is still a small signal compared to the signal radiologists extract when they can employ this selective focus processing and localize the lesions. And my answer to this is that global GIST signal extraction in the blink of an eye can be used in the clinic in a variety of ways that saves lives. One example is triage. When a radiologist sits to evaluate, to screen a radiograph, they have in front of them at least 100 cases to go through within a day. We see that we can go through 200 cases in half an hour and have multiple radiologists look at it at the same time. And maybe by finding radiographs that trigger kind of the tickle bone of both radiologists, could triage these cases. So the ones that are most suspicious go up the stack, and we avoid the problem, more efficient screening, but also avoid the problem of fatigue, which we know affects radiologists and is hard to control for. Another way this signal can be used is that we've seen that we can only, after 9 sessions in some naive observers, we can actually train them to see this signal without them actually knowing what they're looking for. So this perceptual learning indicates that we can find alternative ways to make more efficient training of residents for future radiologists and improve actually performance in general. A third way, and the most exciting, is using this signal as a perceptual risk factor. We know that there are different ways, different indicators of risk, mostly quite expensive and invasive, and for example, genetic testing, whereas this one is very low cost and something radiologists already do. So for example, if again, certain mammograms are seen as having a potentiality for seeing the gist of abnormality, maybe we can individualize medicine and have these patients come for screening on a more regular basis than every 3 or 5 years. So use that as a low-cost risk factor. And lastly, improve AI. AI is machine-driven, and as I indicated, the artificial intelligence is learning something, but obviously something different. There is also a lot of problems with artificial intelligence. It is very sensitive to the databases it is trained on. It can't go across film or digital. It has an issue with whether the digital signal comes from different manufacturers, whereas radiologists don't have this problem. So maybe we can use, understanding this GIST signal, we can use it to improve our AI and make a difference and save lives. So this is all I have for you for today. I just would like to thank you for your attention and also acknowledge all the wonderful people that have worked with me on this. This is a team effort as usual in science, and I want to thank them for their contribution and also acknowledge them, as well as my lab, complex cognitive processing lab, and my funders. Thank you.
Great, thank you, Karla. Very interesting. I feel pretty good now about a radiologist just briefly looking at something. I have to say I'm pretty impressed. So we have plenty of time for questions now to Karla, and you can either use the Q&A box that you find at the bottom in your Zoom toolbar, or you can also raise your hand and ask a question directly. I think we're small enough that we can do that. So who's going to ask the first question? Right, somebody just commented that everything was very well explained. That's why there are no questions, but now there's a question by Jeremy Wolf. Do you think we can get this GIST signal to work as a predictor for other disorders? Beyond cancer?
Yeah, that's a great question. Well, we know that it works across different modalities, so it's not specific to mammography that I've indicated. So whether it is just a general, shall I say, a general signal that there is an abnormality, or it's in some way related to a specific type of cancer, we still don't know. The jury's out and we are using it. We're investigating it. Whether it can go diagnostic in different tasks, I think we can. I think it's definitely the fact that our visual system tunes already to natural statistics of scenes. I'm sure it can tune to any images that we are continually exposed to. So yes, I think yes.
All right, great, thanks. And there's another question. So really excellent stuff. Do you have any specific ideas on how we might leverage your excellent experimental analysis to improve machine learning methods?
Oh, that's another great one. It's a bit of a head scratcher. How do we do that? So there's two different approaches we can go about that. One would be, and this is something that the Sydney lab has done, which is basically take the evaluation of what they call supergisters, so radiologists that are very good at detecting this, and build into an AI system another layer which gives the assessment of those people of the images, then adding additional information. Another way to do that would be by evaluating what are the characteristics, image characteristics that radiologists are sensitive to. Is if we know that it's certain spatial frequencies, if we know that symmetry, what kind of symmetry allows for that perception, what spatial structural regularities give that ability, we can then tune that AI system to be sensitive more to this and augment the performance. And that's what my lab is trying to do, to try take an AI system that is already doing good prediction and try to improve it with adding different layers and adjusting the weights of that AI system. Yeah.
There's a follow-up question, and I think it follows up on this, is if you can elaborate how this can be used for training.
Well, one way we can use this for training is that often radiologists don't just become radiologists and don't just do their work. They're often asked to look for quality control and to train, right? The training is usually always done on a small set of images on which we know the truth, what is the background truth, and usually what is required is that you indicate where the abnormality is. What we're suggesting is that you would add to that training where they would be exposed to a large number of images, knowing that you can assess 200 mammograms in half an hour. You can assume that you can have them train, on many more, for days on end, and have them improve their perceptual abilities of detecting, getting used to that sense of statistical regularities of a regular parenchyma and an abnormal parenchyma. So it is not expensive, it's easy to set up, and it will allow them to see a much bigger set of cases than the classical small number of cases they do to look for quality control. So that's one way of doing that.
Great, very interesting. So we just talked about purposeful training, maybe. And now there's a question by Ben and Barbara, whether if they're not being trained explicitly, just unguided exposure, do you think that would enable a trainee to learn implicitly?
Yes, I mean, that's exactly it. I think there's a lot to be said about implicit training. It would have to be implicit training until we kind of know what is it that they should be looking for. Though we can go to explicit training once we know what are the characteristics that actually expert radiologists are picking up. What is the visual signal? It might always be a little bit problematic for explicit training because it is such a global signal. So it's present in all of the parenchyma. So making the radiologist or pushing the radiologist to kind of distribute their attention to globally pay attention to the regularities will afford them a better ability to do this. If you immediately focus them on small areas or tell them what it is, I think it disrupts this global signal. Same as it is much harder to detect, are you in a room or what kind of room you're in if you are staring at your screen of your computer, for example. So I think definitely both explicit and implicit have something important. My money's more in the implicit training.
So if I can add a question, so I'm wondering, you talked about these supergisters.
Yeah.
Is that like an inborn talent, or is that just people that have had more implicit and explicit training? Is it a combination of both? Is it like more like an expertise, or where would you place those?
Well, based on what my data indicates, though I think we probably should do more kind of detailed research on this, is that these people are most likely people that read a lot of cases per year. Because I think this is a perceptual expertise, and we know that perceptual expertise is something that you acquire, but if you don't maintain it, you lose it. So either use it or lose it. I think what the Sydney group is referring to as supergisters are really people that are probably actively seeing cases on regular basis, people that see up to 10,000 cases a year. So that is where my money is. And I think more work needs to be done on understanding what they refer to supergisters, though. I think they're basically using just the same visual mechanism all of us are using, but their visual mechanism is just more tuned to those regularities than other radiologists are. And that tuning, like we've seen in other cases, there are individual differences in that tuning, yes, but I think they're small. I think what makes the individual differences really much bigger is keeping up with viewing, so keeping up with the practice. So just to kind of, as an anecdote, support this view is that we often find that radiologists that have a lot of experience tend, as they get senior in their career, tend to see read less radiographs per year. They go down to 250 a year, so a small number, right? And you would expect that they're more expert, they would be better. However, if they don't keep up with reading radiographs, their expertise in this task really is reduced. So, and they're not as good as a young radiologist that has just finished his residency and in a year has seen 5,000 of these radiographs. So another evidence towards the idea of perceptual expertise that is gained with experience rather than something special is the fact that radiographers in the United Kingdom have an additional year of training to be able to do screening. And they do screening and they double read, and they're as good as radiologists. So they can be trained to do the same thing, and they tend to see on a regular basis 2,000 to 500 mammograms a year. So.
Very interesting, thank you. Another question just came in the Q&A box. So this is about the timing aspects. So you're looking impressively at how quickly they can do this, but so if you gave them all the time they want, would there still be this difference between, like, or supergister also specific basically to being very quick exposure, or would better gisters also have a higher D prime when they get all the time they want?
Okay, so I don't know about supergisters, but our work, and that's something I briefly talked about, we were under the same impression. We said, oh, great, you can see they can do this. What if we gave them, all the time that they wanted, right? Or let's say more than half a second, go with the first impression, not mask, see what happens, right? And to our great surprise, no, it did not improve their performance. So what you get in that first 500 milliseconds is it. It doesn't accumulate, probably because what happens is that you immediately engage naturally your other system of visual processing, which then means you want to explore the image and you start moving your eyes, and you're now in the focal object identification and localization mode, which leaves the processing of the global characteristics degraded because you're in different mode of processing. And our work on real world scenes would also indicate that if this was really in parallel, you could easily maintain both of these signals. But as we've seen, it is actually serial. You're either in one mode or you're in another mode. It isn't apparent to us because of the difference speed of processing. But it's my belief, and the data would indicate, if you give them more time, it doesn't accumulate. It just goes into different mode of processing. So what you get in that 500 seconds is what that signal is. More time will not give you more, but there's ways we can work on improving that signal to boost it in other ways. I hope that answers the question.
Ah, very interesting. So there was a follow-up question. So that the same person who asked the first question, whether can we say then that registrars are better at their job?
I don't know about superregisters. I don't have that data. It's hard to tell. I haven't looked at that, but that's a good question, right? So if they are the ones that kind of use this GIST signal, you know, if they're better at this GIST signal, are they better at their job? I don't know. I have not looked at that, but that's an interesting question to explore. Most certainly.
And another question came in on GIST training. Would that also make people improve at localization performance?
Pardon, could you repeat that?
Does GIST training also make people improve at localization performance?
I have not looked at that, though my suspicion, and based on some piloting that we're doing, I don't believe that GIST guides attention. And if GIST doesn't guide attention, precisely because you don't have location information, I don't think it would also help in localizing the lesion. So we've done some eye tracking studies where we've present very briefly the image, so we preview it, and then we give a gaze contingent window and see if radiologists would fall, their first gaze would fall on the abnormality, and it doesn't. So I think the GIST gives an impression, which then, as you watch more, as that kind of, you get a general impression, will then guide you, and your knowledge of the structure of the image will then guide your attention to try and find where it is. I think that's the biggest disconnect and surprise, because you think that it guides, but data so far, my data so far, indicate that it does not guide and would not make you a better localizer.
Interesting. Curious disconnection.
Yeah.
So Nathan Trinkle posted a question. Is it possible that there are some cases in which medical image observers will not be able to detect a signal through GIST processing because the signal does not significantly influence the global properties of the image?
Oh, that is interesting. I think yes. I think that a way to test that, I guess, would be to take a mammogram that's normal, right? And then artificially insert a lesion, right? And the question is, if you present it very rapidly, will the radiologists then call it there is a lesion without that global structure? I don't know. That's a great question and a great experiment, and hopefully we'll be able to do that and get back to you with an answer. My feeling is, I think there would be conflict and they would not be able to do it. It's just my humble opinion.
Interesting idea.
Mm-hmm.
Something to run after this talk.
Oh, definitely. It's been on the books for a long time. The problem is, how do you introduce an artificial lesion into a mammogram and not create kind of a pop-out effect? There are many low-level characteristics which you need to take into consideration to integrate it so it isn't just pasted on, right? And it's hard to do that. It's more
maybe with
technical.
some of your filtering options, not as extreme, the low filtering, but maybe that can help make it not pop out. Yeah.
Maybe.
Yeah, but
it's a technical issue. It requires a lot of work and piloting to get it. So I'm, if somebody has a good software that they can, that they've come up with and would like to recommend, I am all ears. This experiment's been on the books for a long time. Just hard to do.
Okay, and there's a question by Alan Badley in the chat. Does this task show a vigilance decrement? If so, would a demanding auditory background, such as music, impair or enhance performance?
Okay, that's an interesting one. I'm trying to kind of think about just performance in general and how it does cross-modally. My feeling is that, I think it probably, I think it would augment the performance. I mean, it's a question that really has to do with cross-modal interactions. And I'm not sure I can make a good prediction because there is really not much work on gist perception and across modalities in the sense of when they're shown together. I know that there is nice evidence from MIT showing that we can actually extract the gist of a sound too. So we have a sense that it's a river or it's woodlands just from from sound statistics. However, how do they work together? We don't know yet. And that's another very interesting aspect. What happens when you have two different signals coming in? Do they augment each other in form of vigilance, as Alan is saying, or actually they interfere because you're trying to extrapolate information from both at the same time? I don't know. It's a great question, though. Thank you, Alan.
More ideas for experiments.
Yeah. Oh, yeah. That's the beauty of giving a talk. You always get ideas for great experiments from different viewpoints.
All right. So I will pass this on to you as well. Someone commented from radiology that this was a really brilliant and teaching talk that you gave. Yeah. So positive feedback coming in. I know in the webinar you don't really feel it, but it's there.
Well, it's good to hear. I feel very alone, staring at a green light at the moment of my camera. So yeah, appreciate it.
So I think we have covered all questions on this. So somebody's commenting that it would be really cool applied to brain MRI. So more and more ideas. Yeah,
it's true. It would be, I think, one of the experiments on the books that we're trying to get is to extend this to other modalities. As Jeremy indicated, is this kind of a general thing? Is it specific to a specific cancer, or can you put it to other modalities? And I think it's important to put it also to other modalities because if this is real, there should be no reason you could not tune your visual mechanism to detecting regularities in any type of images that appear, because they are regularities that happen structural. And our system is, I think, based on what we see in real world perception, very much attuned to detect them and recognize them. And as we see, use them not just for orienting and assessment, but it can be used for other things, for very critical things like satellite imagery, medical imagery, any kind. So I'm very happy to hear about any type of different images that might find the use of this first impression of seeing in the blink of an eye.
Once you do, come back and tell us about it.
Sure.
So yeah, thank you so much. There's another comment in the chat thanking you for the great talk, and Karla Antonelli saying that she enjoyed this very much. I agree. This has been really interesting. Interesting ideas for future research came out as well.
Yep.
So thank you so much for sharing your research and your thoughts and ideas with us. And for regarding future One World CPSs, we will have a bit of a break now. Next month, we'll have the Psychonomics meeting in hybrid format in Boston and online. So we're skipping a November session, and we're also skipping a December session because of holidays and everything. So the next One World CPS will be on January 25th, 2023. And we'll be with Arthur Glenberg on embodied cognition for kids, applying principles of embodiment to education. So I hope to see you there or in between at the Psychonomics meeting. And thanks again, Karla, for this really interesting talk today.
Thank you for the invitation, and thank you everybody for great questions and attending this talk.